Good evening, students. In this class, we are going to discuss about a random process. Actually, we know that random variable is a mapping from the sample space into a set of real or complex numbers. Similarly, the random process is a mapping from the sample space into a set of discrete time signals. Discrete time random process is a mapping from sample space omega into a set of discrete time signals x of n. So, the discrete time random process is a collection or ensemble of discrete time signals. You can understand the meaning of random process and the random variable, right, by seeing this picture. Here in the left side, the picture which shows the definition of a random variable in terms of a mapping from elementary events in a sample space omega 1, omega 2, omega 3, which are mapped into the variables real in a real axis, or it may be a complex axis, complex numbers axis. So omega 1 is an outcome which is available in the sample space is mapped to x1. Omega 2, the outcome which is mapped to x2, and omega I which is mapped to xi. So here the sequence of x1, x2, x3, which is the values of the random variable. Whereas on the right side, the picture shows the generation of a random process from a sample space point of view. That means in a sample space, the same outcome of an experiment, omega 1, is mapped to a sequence of the values of the random variable x. Right? So x1 of n is a sequence of random variables which are represented in terms of samples. So this is a discrete time signal. X1 of n, x2 of n, x3 of n, I of n, which are the discrete time signals. So if the mapping is performed between the outcome of an experiment which is available in the sample space to the discrete time signal, then it is known as the collection of or ensemble of the discrete time signals is called as discrete time random process. We can have different examples for this. The first example, let us consider, the first example is a rolling of a fair die. So the rolling of a fair die, whose outcome of a roll of a die is 1 to 6, the numbers 1 to 6. So here let us assume that the random variable A is selected for assigning the values of the roll of the die. The outcome of an experiment are assigned to the variable A. And let us consider the random variable A, which has values from 1 to 6, 1, 2, 3, 4, 5, 6, with the equal probability. Let us assume that the probability of getting these values are equally likely. That means all the probability of getting the outcome 1, 2, 3, everything are same, 1 by 6, which is equal to 1 by 6. So here, let us consider the x of n is a into cos of n omega naught. Right? So it's this x of n is a random process which can be created with the outcome of the experiment by doing rolling a die, right, which consists of an ensemble of 6 different and equally probable discrete time signals. So if you have the outcomes of the roll of a die at time n, then x1 of n, right, x1 of n is a random variable, and x2 of n, the next one, it is also a random variable, and x3 of n. So the sequence of this discrete time signals is called as a discrete time random process. Okay, so next example. It is a somewhat more complicated process can be generated with the help of this experiment. So here flipping a fair coin may be considered as an example. So when you flip a coin, the value of x of n at time n is equal to 1, right, if heads is flipped. Similarly, by setting x of n is equal to minus 1, which is related to the t is flipped at time n. If flip of the coin at time n is at any time n is no way related to the outcome of the flip of coin at any other time. That means that the x of n is called as a Bernoulli random process. Okay, so here the coin flips are independent, and also this consists of only two values, 1 and minus 1. So this type of process, random process, which is called as a Bernoulli process. So now x of n is a random process which is named as Bernoulli process. Right, the sample function of Bernoulli process is shown in the figure. Right, look at this figure. In this figure, the first part A, shows the Bernoulli process, which consists of the values of x of n with the probability that probability of x of n is equal to 1 is equal to 0.5, and similarly x of n equal to minus 1 is also 0.5, equally likely. So 1 or minus 1, 1 or minus 1. So continuously we are having the output of the experiment flipping of a fair coin. So here the sequence of the random variable is called as a Bernoulli process. Okay, right. And the next example in the second figure, right, the part B of this figure shows the output of a filter, right. So when you do any modification on the process, that will also produce another random process. So another random processes can be generated by transforming the x of n, which is also a random process, by means of some mathematical operations. So if you perform any mathematical operation, here for example we have considered a filtering operation, linear filtering operation. So if the linear filter operation is performed on the x of n, let us consider the filtering operation is defined with the difference equation y of n is equal to 0.5 into y of n minus 1 plus x of n. So when it is performed, the x of n is modified through this filter, and the output of the filter is y of n, which is generated, which is also a random process. Okay, so here the output which shows the second part of part B of this figure shows the difference equation output, right, y of n, which is also a random process. And now let us come to the third example, right? I am giving examples for the random process. So third example is spinning an infinite resolution roulette wheel, right? The spinning infinite resolution roulette wheel. That means the roulette wheel has infinite numbers which are between 0 to 1. And let us assume that the outcome of this experiment, rotating the wheel, which produces the output, which are all equally likely, right? Equally likely, and the outcome is assigned to a variable x, random variable x. Now let us define this random variable x in terms of the binary expansion. If you express each and every value in terms of binary, then it has to be expressed in the form of x of n into 2 power minus n for each value of n, right? n varies from 0 to infinity. So since the wheel has infinite numbers, the ex, right, the random variable ex can be expressed in terms of x of n into 2 power minus n. So what is the value of x of n? It may be either 0 or 1 for all n greater than or equal to 0. Since it is expressed in terms of binary, either 0 or 1 are the outcome, right? For any value which lies between 0 to 1, it is mapped to 0 or 1. So this sequence of binary coefficients x of n, which generates a discrete time random process. Okay, so these are all the examples for the random process. Now you could understand what is random process. Random process is a sequence of random variables, indexed sequence of random variables. So for each random variable there must be an index, which must be the first one and the second one, like that. It is an indexed sequence of random variables, which is nothing but the random process, discrete time random process. Okay, so now let us see the discrete time random process is a mapping from a sample space of experimental outcomes to a set of discrete time signals. So the mapping is explained with a diagram. So here from the sample space, the experimental outcomes are mapped to a set of discrete time signals. So the first signal is x1 of n and the second signal is x2 of n. So the outcome in the sample space omega 1 is mapped to x1 of n, and omega 2 is mapped to x2 of n, and omega I is mapped to xi of n. So from this description and analysis of random process, we can understand one thing. At any particular value of n, let us consider n is equal to n naught. At this point, the signal value x of n naught is a random variable, right? It is a random variable that is defined on the sample space omega. So at n is equal to n naught, and the value of x of n naught is a random variable that is defined on the sample space. The value of x of n naught is defined for the first case x1 of n la x of n naught என்றது the value which is defined, அது either maybe 1 இருக்கலாம் இல்ல minus 1 இருக்கலாம் இல்ல 0 இருக்கலாம், right, which is defined by the outcome of an experiment omega 1. So omega 1, it may be an outcome of an experiment rolling a die or flipping a coin, or it may be a rotating a wheel. Okay, so எதுவா வேணாலும் இருக்கலாம், and the omega 1 is the outcome of that experiment, and the corresponding values for the omega 1 is represented here as a signal. Do you understand? So at n is equal to n naught la the x1 of n அப்படினா x1 of n naught அப்படின்றது the value of the random variable, right? Random variable x oda value which is defined on the sample space by omega 1. Similarly the next one x2 of n naught என்றது அந்த random variable oda value, அது வந்து flipping a coin na ht அப்படி இருக்கும். x3 of n என்றது rotating a wheel na it may be from 0 or 1 ஆ இருக்கலாம். First one வந்து rolling of a die na it may be 1 to 6 value. Do you understand? So each and every outcome is mapped to a discrete time signal, and this discrete time signal which is combined together, and it is called as a random process. So random process is an indexed sequence of random variables. Okay, so random process here which consists of x of minus 2, x of minus 1, x of 0, x of 1, x of 2, right? Each and every x of minus 2 is a random variable, and x of minus 1 is a random variable. Okay, so which has values corresponding to the experiment outcome, right? Corresponding to the outcome of an experiment. So when they are indexed together, it is called as a random process. Now is it clear? Right. So each random variable in the sequence has an underlying probability distribution function. Underlying probability distribution function. Because we need to express the random variable, the characteristics of random variable only in terms of distribution function and density function. So the probability distribution function corresponding to the random variable x, which is denoted by f of x of n of alpha, fxn of alpha. Let us write fxn of alpha. So here, which is expressed as probability of x of n less than or equal to alpha. And similar to that, the probability density function is the derivative of probability distribution function. So fxn of alpha, small fxn of alpha is equal to d by d alpha of fxn of alpha. So with this, not only this probability distribution and probability density function, if you have more than one random variables, then we need to express with the joint probability density function and joint probability distribution function. So they can be expressed, joint PDF and joint probability distribution functions can be defined only when we define the collections of random variables, how they are related to each other, right? Here in the first two expressions, this fx of n and fx of n, which gives information about only one random variable x of n, right? X of n. Whereas if you have more than one random variables, then how they are related, based on that only we can define joint PDF and joint probability distribution function. So the joint distribution function can be expressed like this: f(x1), x of n1, x of n2, x of n k with alpha 1, alpha 2, alpha k is equal to the probability of x of n1 less than or equal to alpha 1 and x of n2 less than or equal to alpha 2, x of n3 less than or equal to alpha 3. Like that, it is to be defined. So the required joint distribution function is for any collection of random variables x of ni, which is defined here, for any collection of random variable x of ni. Now, depending on the distribution functions, there are different types of random processes can be generated depending on the distribution functions. So here we define the distribution function for random variable. So and the joint distribution function also defined. So depending on the distribution functions, we can generate many different types of random processes. And different types of random processes can be generated. It may be a Gaussian random process. Depends on the distribution, right? If the distribution is similar to the Gaussian, if it is generated by Gaussian random variable, that means a sequence of Gaussian random variable will generate a Gaussian random process, right? And if the random variables x of n are uncorrelated, right, then the process which is generated by the uncorrelated random variables is known as white Gaussian noise, because it is very random, noise-like sequence. Okay, and on the other hand, if x of n is equal to alpha, where alpha is a Gaussian random variable, then each random process in the ensemble is equal to a constant for all n. Okay, so you can get different types of random variables depending on the distribution of the random variable, distribution function of the random variable, and different types of random processes can be generated. Right, now let us look into ensemble averages, the first order and second order statistics of the random processes. Okay, so here a discrete and random process, since it is an indexed sequence of random variables, we can calculate the mean of each of these random variables, the mean of each of these random variables, and we can generate the sequence mx of n, which is equal to expectation of x of n, which is known as the mean of the random process x of n.